Sometimes the analytical techniques that we have so far don't work. Either we can't direct substitute and we can't use the dividing out technique, we can't rationalize the numerator. So another tool we have that potentially helps us out with things is something called the Squeeze Theorem. Now the Squeeze Theorem is notoriously hard to apply. It's really hard to find the functions h and g that are mentioned that work and will allow us to find the limit of f. We're going to show you two examples. You'll see them a little bit later in this lesson as you work through in Moodle. But I want you to understand that mostly what we're interested in here, other than being able to play with those examples a little bit, is to have an understanding of what the Squeeze Theorem is and how it works, so that when we encounter it and talk about it again and actually use it to help us understand some calculus later in the integration section of the course, that you have an idea of what it is and how it works and how we get to the conclusions that we do end up drawing. So to help you understand the Squeeze Theorem, I've drawn a graph here. This is some function f of x, and for some reason f is not defined at c. There's a hole in the graph. We'd like to show that the limit of f is L, and we haven't been able to do this through direct substitution. The function's not defined there, and we haven't been able to use a dividing out technique, and we haven't been able to rationalize the numerator. So we're going to attempt to bring into play the Squeeze Theorem here. So in order to make the Squeeze Theorem work, one of the things we need is a function h of x, which is always less than or equal to f. That is, it can touch f, but it can't ever go above f. So maybe it's a function that kind of comes up, touches this point, stays underneath, and comes down like this. That'd be an example. What we're hoping happens with h is that its limit is this value L when x approaches c. So I've drawn it to do that. We also need a function g. G is always going to be above or potentially touch x, but it can't ever go below x. That is, g will be greater than or equal to f. So maybe g kind of comes along and does some stuff like this, eventually hits here, but comes back out and does something like this. So g of x is always staying above f, at worst it touches it. H of x is always staying below f, at worst it touches it. And then we want the limit of g of x as x approaches c to be L. We also want the limit of h of x as x approaches c to be L. And since f is always somewhere between f and g and h, again, since f is always somewhere between g and h, specifically at c, it gets squeezed in between the values of g and h. Their limits are both L. F is in between. So the only place it can go is to have a value of L. So this is the basic idea of what's going on with the Squeeze Theorem. We have a function that we're trying to evaluate its limit. We find two other functions that have that limiting value exactly at the value c that we're interested in. One function stays above f, one function stays below f. Again, they could both touch it, but that's as worst as we can get. And therefore, when we get to c, everything gets squeezed, or I shouldn't say everything, f gets squeezed in between those two functions. And that helps us to prove analytically that the limit of f at that point is L.